It's a pleasure to have with us today Dr. Mertoguno, whom I've known for a very long time, since I was in his Ph.D. thesis committee many years ago. Let's say that's before I came to Greece. It was when I was still living in the United States. Dr. Mertoguno had a stellar career since then. He has worked in the Silicon Valley in various companies, and now he is in the Office of Naval Research. And he is going to talk to us today on a very interesting subject, which involves security, cyber-physical systems, and in general, how to deal with systems. And that's actually an area that MHL is very interested in, and other divisions of the School of ECE. And so it is excellent that he's coming to bring his expertise on digital system design and computer security. So without much further ado, Dr. Mertoguno. And since I'm here and we have one more minute, I need to point out that Dr. Mertoguno is here with Professor Bourbakis, that many of you know. And if you want to meet him afterwards, I'm sure we can arrange a meeting.
So this is the first three slides are kind of a mandatory slide that we have to use whenever we present outside, and this is just this year. So ONR want to do some kind of awareness to everybody. So I manage cyber security and complex software research program at the Office of Naval Research, and we got some budget from the Navy that we do basic research, mostly doing with universities, and applied science research also. Where there are some companies, but still mostly universities. Okay, so the Office of Naval Research has 400,000 plus people, and 2.1 billion, but that's of course for building ship, etc. So that's not too much. And a small part of it is used by research. But the research is actually quite big. Within that, there is the ONR Global, which is in Europe, also in Prague, in London, I think one in South America, there's one in Japan. Then the Navy has the lab, which is NRL, this one, which is our lab, and this one is kind of the offensive, kind of the cyber operation things that are more civil. In terms of the research that were funded, some of it is very narrow, very short term. The other is very broad and long term, long range, which this discovery and innovation is the one that I belong to. And I have a small budget for doing cyber and software research. So when I first joined ONR, I had kind of have to kind of see make some kind of vision what I want for ONR, how to drive the research to work. Right? So the first thing that I see is a lot of the IP is operator intensive, right? And because of that, and also it has a lot of vulnerability. The fact that the cyber, especially in cyber, where a lot of the attack is basically automated or partially automated. Now, if you have to rely on human, it's always too late. So that's part of the reason why our current cyber action or operation is mostly forensic, because we can only do it after the fact stuff. Normally 6 months after the fact. So that is the biggest problem. How, if we can close that gap or close that loop faster, then we're probably in a better shape. But in order to do that, it cannot rely completely on human. So the concept would be more of a human on the loop rather than human in the loop. So we would like to do some automation. Of course, a lot of people are scared about that, but that's we're pretty useful. So we don't have to kind of get something that people can be trying to do. So the goal is to have a secure and dependable information infrastructure with minimal babysitting. That's what. So in a way, it's almost like treating a computer like a robot, right? Robot can adapt to itself. Why can't our computer do it? I mean, computer is used to control a lot of stuff, but it doesn't control itself. So what's the root of the issue is that in cyber environment, it's very asymmetric. It's much easier for the attacker. It only has to pick one thing, and it can try it so many different times. Well, the defender has to be right all the time, right? And the fact that our systems are static at this point, at least, and homogeneous. It make it easy to target. They can practice outside before they attack, right? And where they are very opportunistic and kind of have time to do their stuff. I mean, it's very difficult to kind of catch the attacker. The attacker can only have to need to break one, and the defender has to be successful all the time, right? Which is kind of asymmetry there. And then our system itself, the current system is very vulnerable. The vulnerability based on the user. I mean, there are a lot of problems with that. And there is the protocol and the policy and the software, mostly the software, right? Most of the common problem is software. But if there is a problem with the hardware, if there is a Trojan in the hardware, it's very difficult to do anything, right? So there are a lot more vulnerability in software. Software is very vulnerable, but if hardware becomes vulnerable, then nothing software can do pretty much. And the fact that we use a lot of code, which is common as the shell component, that makes everything worse. The use of code itself is not the source or the root of the problem, but the reliance on it makes everything worse. Because the codes were not built for military. I mean, it's built for public and enterprise, where a lot of things can be tolerated. So what can we do? Well, to create the to address the asymmetry, one thing that we might be able to do is not to make the environment very homogeneous. We could introduce artificial diversity, and people are start doing that, right? I mean, address space layout randomization is one thing, right? But there are other diversity that can be applied. And to address the vulnerable system as well, if we can, most of the current vulnerability has its root in software. Part of it is the discipline in software is very low. Now, can we create a development environment that can help the programmer realize problem earlier when they are coding rather than later on, and when they already forgotten what they did. So that's that. And then, of course, we need a system that can deal with partial failure. So the way we look at it is that we look at it from the innermost, which is the computer itself, and then the interaction among a user and the computer, user and user, process inside the computer to another process, across the network. So there is that. That's the, and then the last one is the plumbing itself, which is the internet. Currently, I saw a lot more research on the internet side, on the plumbing. So because of that, we say, well, if there are a lot of people funding that, we probably shouldn't, right? We probably should focus on place where we can develop something new, or we can make an impact. Because whatever amount of money we have, if we send it to the big pool, it really doesn't make any effect, right? So that's part of the my strategy to basically address that. Drive it where there isn't much research. So in that case, we kind of concentrate more on the host side, especially trying to make it autonomic and self-awareness, etc. We also do some. We have all of the research in everywhere, but just percentage-wise, we have a lot more on F1, a little on F2 and F3. On the F2, the current thing that we push is actually automatic vector function generation, where we kind of use computer to generate a new cryptographic algorithm by itself, right? So this is kind of the global thing that we have. Each of them I have a backup slide that can go detail, and there are some that is not here. So the first two, 1 and 2 are autonomic computing. I'll talk about it later more. And then number 3 is kind of trying to turn a single computer to look like a subnet. And it's kind of a honey net, but the trick is how to make it cheap and high fidelity. People use this kind of system mostly to watch attacker, but that's not what we're going to use it for. We're going to use it as a decoy and also to deploy disinformation, meaning sending wrong information on that side of the fake subnet. So that's that, and then the automation in cryptography, we basically the cryptographic function like SHA or AES or something, it's very difficult to do. To design. It has a lot of math, and there are a lot of points to make mistakes. And people don't believe that it can be automated. We give that challenge to some of the PI, some of the professors, and we currently have basically somewhat successful here. There are 13, 14 publications. These are in conferences like CCS and crypto that is doing this. And those are all our funding actually. The only people who are doing this right now is within our program. There is nobody else yet. But so here is that the trick is that to change the design process into generate bunch of stuff heuristically or randomly, and then as you generate it, you note how you construct that algorithm is constructed. So first of all, look at a certain mathematical field, and then create some kind of heuristic to basically create something that might be secure. And as you create that, kind of also say how to or make a formal definition of how you construct it, and then you send it to theorem proof. So we turn design's effort into basically generate and proof or search and proof, right? So part of it is something like that is usually amenable to computer, which is kind of dumb but relentless. So that's what we do. So currently the key player here is actually Spain, IMTEA, which we funded through collaboration with Stanford and UPenn. So there are opportunities for funding in Europe, right? Yes. How great. We fund them directly, sometimes through ONR Global, but some of them directly. Yeah. So that's automation in cryptography. The tools that is being used is something like ECE TUC, right, which is based on block. And then some other team at Johns Hopkins use SMT. But so that's what we do. And then we go to number 6 first. This is saying that, well, programmers make decisions all the time in code, because otherwise it's going to get automated, right? If it is completely prescriptive when you use a programmer. And what we see is there is a gap between what is the spec, what the programmers need to write the software for, and what is in programmer's head, and what is the actual code. These are some concerns out of sync. So this one is trying to kind of close the gap between what is in programmer's head and the code, right? It doesn't close with the specification yet. So the idea is as people are coding, extract some knowledge, present it back to you. If you see something wrong, that means there's a gap here. Either the software make a mistake, his code has a problem, or he's imagining something that is not actually the code. Okay? So if he fix it, either he fix the things that we extracted, the graph, or he fix the code, then you kind of close the gap quickly, right? You close it as people are coding, so that they don't forget. Because we see that the major time is spent on debugging, basically, right? Verification. That's another thing, right? People claim that verification effort is 6 times of the development. And we are doing it, and there are a lot more research on the verification, so that's the reason we're not looking at verification, looking at the development side, and also the development side is actually upstream to the verification. So if you create something that has less bug to start with, the chances it's not 6x. So and then we start actually. I'm probably better off going to the backup slides. So this is the driving force. Right? The Moore's law continue, Tanner's law stop. What that means is every a year and a half, you double the amount of transistor, but every transistor you did not half the power. So you end up, and you see from physics that every square millimeter of silicon has a maximum heat that it can dissipate. Right? Beyond that, it's going to burn. So that's create a condition where current chip, there are actually the trend is that more and more chip has the percentage of usable transistor at every given cycle is dropping. Percentage is dropping. The number of transistors that can be used is going up, but the percentage of transistors that can be used at any cycle is dropping, right? Because of the fact that you get double, but you don't get the power half, so you kind of.
But that has been the case since the 1950s, exactly. Because when you had a very small computer, it was confused, and as you got bigger, well.
Right, but it hasn't reached that point until like point something, right? Point 1.4 or something is still linear, and some after that. Right? So it's linear, somewhat linear, and then flat. Part of it is when it gets smaller, you kind of have to reverse bias the transistor and everything. So you don't get the saving in power, there are a lot more leakage, now your static dissipation is higher than your dynamic. So that basically creates a problem there. Multi-core, even multi-core, well, that makes people move to multi-core. Now you have a bunch of stuff that lower clock speed, so it doesn't, because the clock speed is proportional to power, so by distributing the power across multiple things, it's more, they can sustain more, but that's multi-core, right? But even that will stop because, there is a natural limit on parallelism. For any given problem, there is a natural limit where you can create a parallelism. Beyond that, you have to do speculatively. But speculative it might be good for performance, but it's always bad for efficiency, right? Because it always costs you something. And in this case, where the problem is efficiency, basically the speculative is kind of counterproductive. For that, then what's next? Maybe more into heterogeneous multi-computing, right? That's what the design can be moved that way. So you have a bunch of cores, but each of them are efficient on a certain way. So if you have the same core, right, and you have a limit. you have a limited number of parallelism and also limited power, you end up having a problem of, let's say you have a chip of 100 cores, but at any given time you can only turn on 25 of them. If they all looks the same, does it matter, right? So 100 equal to 25. But if they are heterogeneous, then it may not be 25, but even if it is 25 of different type, which are more which different level of efficiency for a certain problem is still a lot better, right? So you can sustain the throughput better or performance better that way. So now the problem with heterogeneity is programming. Designing it in terms of chip architecture is not very difficult, but people are not used to programming. People who program high performance computing, the mathematical type of problem, they could do that. But most other programmers, they cannot, right? So that's something we want to address, right? So if that's a driving force, what can we do, right? One is probably make an integrated programming environment that can deal with it, right? People doesn't have to look at the algorithm, break it up into pieces and make it into different hardware, right? Which make it even worse. Right now, if you have a graphic processor you want to use, you have to write C and CUDA separately. That's what we don't want. We want a single source code, whatever it is, and the compiler that is smart enough to basically identify the chunk and map it to the appropriate resource. Of course, that for optimal, that's probably going to be hard, but we don't need to get optimal, right? We only have to get good enough.
That software, the single software, is it something like meta software that goes to CUDA or to C or to something like that?
No, it's a single source code. Right?
Single software for everything.
Yes, it's a C, so a variant of C or any language. I did not specify what language. Currently, we have a project that does this.
Does it have enough expressive power to handle everything that you want it to do?
You know what? The team actually use a lot of machine learning to kind of guess. So how optimal it is, we don't know, but at least it works. Right? At this point, right? It can be improved further, but at least it's we can do it at this time, for limited. So currently we have if you guys know Popcorn Linux, those are actually our project. We funded that. We started that. The guy come to us wanted to do formal verification, and we said, well, we don't do verification. So here is the problem. What can you do? So he did that. So Popcorn Linux is basically an operating system, Linux, that is multi-kernel that creates a single, looks like a single operating system abstraction, but actually underneath it, there are multiple different instructions, and this operating system, if you have a program that has been compiled using, so this is Popcorn Linux plus its compiler. And compile for Popcorn Linux, it's actually, each of the threads within that program can be spread into different architecture that is supported. So currently it supports Xeon and Xeon 5, which is still x86 with different variant, and also ARM and GPU. Right? And it's released freely, so you can see what you can do. I mean, the one that is released is probably still the initial version. The ARM is not complete yet, but they demonstrated to us for ARM.
And these are publicly available?
Yes. So we have that's Popcorn Linux, and then dealing with basically compile it, you chunk it, and you kind of compile it again for the particular architecture, and then you have to bridge all of the data movement. Right? And what is the strategy? If you move data too much, the performance is bad and all that. And currently they use machine learning at this point, at least, for the compiler. And then, so efficiency also becomes more important in future software. People, especially when it comes to CPS or control system, where latency is a lot more important than actually throughput, right? Because latency predictability is kind of a key parameter. Throughput is you usually kind of you can put a lot more hardware, but not latency. Right? So now the trend with the multiprocessor is actually bad because it creates a lot of disturbance, right? Because it shares the same bus, it shares some caches, right? So you have a lot more collision, your latency is really unpredictable. So there is research on that too. So that, and then the last one is for this area is that we also think that software needs to be a lot more efficient. So there is a paper from IBM just to move a single date field from SOAP to Java, it created 268 method, and it generates and destroys 70 objects just to do that. So that's why that growing, right? Our current modern software is a look machine. It's doing something really simple and very complicated stuff. And this is probably the problem with object-oriented, taking into extreme. And so current software is very complex because this was developed during time, and during that time, historically, decisions were made, and that was the correct decision at the time. But things change, and nobody revisits the condition, the assumption. They keep on building things on top of what we have. Right? So, if you have a library, some program called library called library, or library called library, because it's all platform, it's all built on one on top of the other. Very small percentage of the code is actually being used, but the entire code is used, right? So I used to say that things that we don't use, we can never test unless you do parsing, but your adversary can use, right? So what can you do about it, right? So the things that we want to do is actually, if you have something like that, can you treat a library as a source code, meaning that kind of cheating, right? Just-in-time compilation of a lot of stuff. Can you just grab whatever you need from the library, create a shadow version, and don't use the library, use the shadow version. So we have an effort doing that, right? So when you start doing that, you have an API with 5 parameters. 3 of them are fixed. You can do constant propagation, strip whatever code is not needed, right? And once you do that, a lot of the procedure call becomes just an empty wrapper that can be removed also. And that removing the code load size doesn't help performance very much. It helps a lot in security, but not efficiency very much. But when you start removing the layers, and that's where the efficiency gain can happen, right? Because every call you have to say a lot of stuff, and people don't realize that. Right? So that's what we want. I mean, the only result that we have right now is
But that may affect the memory footprint, won't it?
Yes, loading now you load something small, right? Which is good, and also, but there is the trade-off is that now if you specialize everything, you have to store a lot of small things, right? So your total storage space might be larger for execution, but that might be okay, right? I mean, what is the size of the executable currently as compared to the data and stuff? I mean that. So for some area we might not be able to do that because there's no room for that. But on those applications, it's usually very efficient to start with. Right? The one that has a lot of load is the one that's in the enterprise world where people don't care about anything. The only result we have right now is Jan Vitek at the Northeastern. He did this on R language, and he actually get this 8 times speed up, right? Meaning that basically having a single processor looks like you have 8 processors. So it can be significant, but it's also difficult, right? Part of it is we have to do with binary.
So the speed up was just from pushing library calls?
From actually streamlining the engine, the R-line engine itself. and removing the bloat there, and also reducing some of the dynamicity of R as it gets run.
So, but also from within the code to the code, not only to the libraries.
Yes, both. So this is actually both, but I'm talking about library right now because that's the one that is probably a later issue.
Probably need to get also in the AI.
Yeah, okay. So we have this. So this is, okay, what else can we do next? So the AI is, well, to initialize it. So this is what I talk about autonomous computing. What we want is a system that basically, you know, the foundation of it is actually, the foundation of it is, well, the foundation is actually self-awareness, right? Knowing your own state is the big difficult part. This is a system that goes the loop, sensing its own state and react to the environment. Or computing as a robot, sometimes say. The action part is easier. The more difficult is actually understanding what you do. So in this kind of stuff, real-time decision making is very important. And to do autonomic decision making, that means that we have to know our own state, knowing the state of the environment, our environment. We have to be able to anticipate what is the change in the environment, and also being able to project if we do something, what happened in the environment and our own state, right? So that's what we do. Something like this is required in a lot of the automation from, you know, underwater, UUV kind of thing, or drone or robotic, and also in our autonomic computing. Current autonomic computing is only looking at formal, but we know that to make it really, to really make it work, we probably have to deal with statistical also. Currently it doesn't make sense. So the current state and the state and the model for extrapolating into a future state is required for this to make a plan. So, and what human has gut feeling. Human has a deliberative thinking. Gut feeling is things that we know something, but we really don't know where it comes from, and we cannot analyze, right? It's usually and it's usually fast, shallow, and reflexive, right? It just comes up. And then there is a conscious decision making that we make, right? We do if-and-else analysis. We project something, right? So that's slower but deeper reasoning, and make a deliberative action plan. Right? In the other area, there is a theory and model built for this. You know, one that gives us inspiration is actually by Daniel Kahneman, Thinking Fast and Slow in the System Model. So we think that, you know, decision and plan is a result of interaction between intuition and deliberate thinking, between the gut feeling and our more formal thinking. And it is an interaction, right? So it's basically some kind of a loop. So we can conjecture that, you know, if you don't have time, so you probably have one. You don't make that many loops, but if you have a lot of time, then you probably make a lot of loops, right? And in the world, there are other things that has two systems like that. Like the immune system also has two different components that kind of complement each other, right? So, so if we look, you know, in the old days when we do AR, it's mostly about rule-based, knowledge-based, right? Now everybody is doing statistical, neural network, HMM, LBA, whatever, right? Those are all statistical completely, right? So the definition here is between formal and statistical is if the knowledge base is in the form of rules, whether or not you have probabilistic number of values, it's rule-based or formal, because there is a formal specification for each of the concepts. When the knowledge base is represented in set of weight, just numbers, and those are completely statistical, right? If you look at it, the statistical is faster in inference, forward inference. Learning can be slow, but forward inference is fast. And then formal is, it has to go through a loop of multiple different, exploration of all of the rules. So it's somewhat slow, right? Formal is constructed with the symbolic representation of the world, while the other is just learned from the world, the sampling. So the sampling quality matters. A lot of people sometimes do machine learning, and then they don't realize that the model that they learn may not apply anymore, right? So environment has drift, they kept using the same model. And the problem is that you don't know. You don't know when it is, when the model becomes stable. And if you keep on training the learning, there is a danger that somebody can corrupt you. Right? They can play with the distribution and shift it to the way. The formal has a lot of structure. The other one is flat. Formal is relatively rigid. It's very difficult to come up with the new rules. Somebody has to insert it into it. Where the other one, it really doesn't care about rules, right? It's just create an abstraction. So the formal can be analyzed, and you can see the intermediate result. You see how you get into the, you derive your conclusion, but the other one you can't. So we map this into the formal is more like a deliberative thinking, and the other one is our calculation, right? Statistical is more like calculation. And here is the. So we said earlier that we have to sample, we have to make plans, right? So if you try to use formal for sensing, you quickly run into the combinational explosion, right? Because the detail at the very low level is very large. But it doesn't mean that if you know a particular thing at detail level, you cannot use it, right? So there could be something that we can carry all the way down. But for planning, the knowledge structure and everything is great. While sensing is very good at the lower level, it's great an abstraction that we don't, and recognize a certain class. But if you imagine if you want to use something like that for planning, imagine you have a decision tree. So every possible path in that tree has to be recognized, or it has to have a class. That tree, and the number of class, the number of possible paths within a graph is much larger than the node or the link. So you end up into a combinational explosion also at that point, right? But it doesn't mean that for a particular fixed path, you cannot learn. You cannot create a class to recognize just for that path. So if you look at them, they are kind of complementary, right? But this is what people have done. So on the statistical, you have something like deep learning when they create a layer. There is some structure that they can get, but it's very limited. And then on the other hand, if people's putting probabilistic into the form, Bayesian Markov logic, etc. What they do is basically they use a single knowledge representation for everything, right? Either rule or just rule. So, as we said earlier, that one is kind of complementary. So why can't we stop them, right? We can use the statistical for sensing and the other for planning. The problem here is that we create an arbitrary abstraction layer or definition where each of them cannot cross, right? I mean, there is a case where if you know something really specific, you can use a formula to do that for part of your knowledge, but maybe not all of it. The same thing, if you have a particular plan or path in your planning, you can use a statistical to point it. But this structure doesn't allow it because we create a rigid boundary. So what we think is that it might be actually to have two overlapping systems, right? Where the overlapping is where they interact. So that the is on the other side. This thing then it's going to allow for for some formal to go all the way down, or some of the statistical to go all the way up. So the structure would be kind of have two systems independently or semi-independently kind of interact. That's what we kind of try to do. So the goal is synergistic integration toward decision making. We want them to be somewhat independent, and we would like to integrate functionality rather than knowledge representation. The thing with unifying knowledge representation is, yes, you do gain all of the benefit from the statistical and the form, but you also inherited all of the disadvantages, right? It's still limited, it's still rigid, right? It's still, so you get all of if you combine the knowledge representation. Here, in order to interface or to interact, you need some kind of interface with the overlap of the knowledge, so they can have correspondency and can work that way. So we would like to keep the underlying knowledge representation independent. And this is actually a weaker requirement, because this is also saying that not all of the formal, node in the formal has to have a statistic representation. And otherwise, statistic can have their own interpretation somewhere else, right? So hopefully, if something weaker could be cheaper. I don't know. I mean, that's still to be studied. And the thing is, we want them to kind of interact and then, kind of correct each other if there is a conflict. How do you resolve the conflict? And how do you transfer knowledge from one to the other, right? And then, how to use the formal to guide the statistical, and to patch hole on the rules with the statistical, right? So here is potentially, how we can do this. Let's say you have a if you stack it, what you have something of formal, some kind of graph up there, knowledge graph, and then you have everything that looks like a cloud is statistical. The one that is kind of stacked cloud, this is probably deep learning or two statistical you put together or something like that, right? And then the interface is defined on the green node, right? That's where you transfer knowledge or you transfer concept from the statistical to the formal. What we want is that overlap is that the statistical can go everywhere, right? Not only at the leaf node, but this will create a conflict. And we need to solve the conflict, right? I mean, so conflict resolution becomes important. But also the fact that it can create a conflict. This is also the fact that the knowledge can grow. I mean, if we have a system that never creates a conflict, it's basically complete by itself or ignores the rest, right? So it can never grow that way, unless you insert a new one.
Not complete, consistent.
Consistent. Well, not complete, consistent. I don't know whether it's consistent within itself. From its own self, it's consistent within itself. But it may also be not accurate, right? So this is potentially one way to do it. There might be many others. So if we do something like that, I mean, so how far would we want to carry it? When I draw it a graph, but it's actually a tree, but it's actually a graph. It's easier to draw a tree. Drawing a graph will create a mass quickly. And then how currently on this diagram we only look at the other way. We only look at this, right? Or this. But we can also fit this into here, right? Or fit that. Or how complex can be so? I mean, when is good enough? Where is the diminishing return? There are a lot of things if we start doing something like that to show. And it's a lot of research that can be done here. So this is basically almost all. So also that each of this statistical or formal doesn't have to be strictly formal or strictly statistical. You could use deep learning here. You can use something more hybrid. You can use Markov logic network here. We don't know. I mean, what's good? It probably depends on application. And yes, so this is the last slide. Some before the time. I stole this diagram from somewhere from the web. I think it was a note somewhere where I stole it from. and then I cross out things that I don't care. Make some modification and I set those stuff, right? And then there is something here about heuristic that I did not discuss. So where is it? Where is this heuristic? Is it here? Is it there? It's difficult to make it here, I think. I don't know. For formal, yeah, it could be formal, a generalized rule, you know, a system where you ignore some of the parameters or you approximate some of the parameters, or you put a constant on some of the parameters. Right? Or it might be unnecessary at all. Maybe you don't need it. The two systems can do it. That becomes also. So that's about it.
We have a little bit of time for questions, if there are any.
How much do you expect from this interaction between the reasoning and the statistical to produce results in the sense of accuracy of events, of representation of plans? That means if you use the two techniques and you combine them with one scheme that you say one a pyramid, one on the top of the other, it's going to generate some results. Are you going to reverse this, put the other around?
Yeah,
at least to reverse the roles, something like that.
Yeah, currently.
And to use combinations of them.
Yeah, currently we funded some research project doing this. We kind of talk to people. Are you interested in doing something like this? Yeah, there are. So there are some research. It's not that yet, right? Because it's nothing like that. It's very difficult to get there. So right now there are some results where people are putting one on top of the other. Actually, by the result so far is that the precision that it generates. I think the one that has been done, I think formal on top of at the bottom of statistical, right? For formal initializing statistical. So you have a system, I think some kind of a vulnerability classification, which is completely statistical, but you initialize it with code analysis. That actually already improved the performance significantly and precision-wise.
Wow.
So in theory, right? I mean, the statistical should be able to do it. The problem is then, then how much training data do you need to provide to reach that point, right? By jump starting it at a good point, it's actually can be quite a bit. And the other person is doing HMM, and they initialize it also with the code analysis. And the same result applies. The improvement on the precision is significant. And even when they start analyzing it, they saw that the one that the HMM that they initialize it from formal has I think the 2.9 something on average hidden node. And if they didn't do it, it doesn't reach that point. But when they actually expand the number of hidden nodes just through training, at the three hidden node, it's still worse than the one that they train, and it gets a little higher hidden node. When if they move it further up, it actually the performance actually drops because it's probably overfitting or something. Right? So here we see that a case where you start with a good point, you actually get a better local minima, maybe if not global minima, right? So in theory, the HMM itself should be able to get rid of it, but the problem is your training set may not be required or may not be sufficient to get it. And so doing that is improving. I think the other guy who is doing SVM, I think it's SVM and some kind of code analysis called trace analysis. They're going to reverse it. They're going to put the formal on top and put statistical at the bottom. Once you start doing that, then now you can stack it, right? When you stack it, it becomes more interactive like that.
But then it's more difficult to prove that it works, right?
It is. I mean, so how it's a lot of unknown.
It keeps us busy.
Yeah.
Any other questions from the audience? No? In that case, we'll thank We will be available for a little bit if you would like to have discussions one-on-one for a little bit. And the same is true for Professor Bourbakis. We may go for lunch later on if people would like to join. And we'll go from there. Okay? So we'll play it by ear. Come find me if you'd like to have a meeting.